What came before the Big Bang was never supposed to be calculable. It was meant to be a wall, a mathematical do-not-enter sign painted in infinities so violent they broke every equation we trusted. But here's where everything snaps. Modern numerical relativity has finally started pushing through that wall, rewriting Einstein's equations at resolutions the original theory was never designed for. And what those simulations are revealing is not silence, not nothingness, but a roaring, churning, unstable pre-cosmic state that behaves nothing like the clean, smooth beginning we were taught. It's messy, chaotic, violent. And the strangest part is that this state wouldn't even count as a beginning. It's a continuation of something older. But before we even settle into that idea, everything breaks again. Because the moment you remove the classical singularity, the whole logic of a universe that starts collapses. The simulations show that if you evolve Einstein's equations backward using high-precision numerical grids dense enough to capture tiny curvature gradients, the curvature doesn't blow up. It plateaus, then it bends, then it reverses. Suddenly, what looked like an inevitable singularity becomes a phase transition, a bounce. And if there's a bounce, there was something before. But that creates another problem. What kind of universe can survive being crushed to densities trillions of times higher than the core of a neutron star, only to expand again? Standard homogeneous models collapse instantly under their own symmetry. They break apart, form caustics, and die. The only early universe setups that survive backward evolution through these new simulations are violently non-uniform. Nothing like the traditional smooth, symmetric FRW universe. Instead, they're full of gradients, clumps, local curvature spikes, directional distortions, the opposite of the perfectly smooth beginning narrative. And then it gets worse. Some of these non-uniform states evolve forward into a universe that looks statistically indistinguishable from ours, which means our universe could have begun as something deeply irregular, deeply turbulent, and definitely not nothing. But here's the twist. You can't get inflation to ignite in most of these messy initial states unless a trigger mechanism kicks in. Something has to spike the potential energy in just the right way. Some fields fizzle out too early, some blow up too fast. Some refuse to smooth the universe at all. Numerical relativity lets physicists crank through billions of initial configurations at high resolution. And across those runs, the universe only inflates if certain fields hit narrow windows of density and curvature. If the inflated field misses those windows, the universe doesn't get big. It stays tiny, dark, cold, and collapses back into a crunch. But one class of configurations keeps working, and that's where the story violently pivots. The same pre-bounce conditions predicted by loop quantum cosmology. Because in loop gravity, space-time becomes discrete at Planck scales, not fluid, not continuous, but granular. When densities climb high enough, quantum geometry effects create repulsive gravity. Repulsive. A force that resists collapse so aggressively that it prevents singularity entirely. You don't get infinite density, you get a minimum volume. And as the universe contracts toward that minimum, the repulsive term skyrockets and slingshots the universe outward. That slingshot is the bounce. But here's where everything shatters again. String theory predicts something completely different, yet equally explosive. Not a bounce, but a pre-Big Bang vacuum. A super-dense, super-coherent state filled with evolving strings and branes in extra dimensions. In this picture, our Big Bang wasn't a beginning at all. It was a phase transition between string, vacua. Space didn't appear, It reorganized. Dimensions didn't form, they rearranged. And just when that starts to settle, string theory drops the brutal reveal that some versions predict a pre-existing contracting phase too. Different mechanism, same conclusion, no singularity. But if you think that's stable, wait, because the brane collision models raise the stakes again. In these models, our universe is a three-dimensional membrane floating in higher dimensional space. And the Big Bang was the impact event. A collision between branes that released unimaginable energy. That collision didn't just heat the early universe, it replaced the singularity entirely. Which means the event before the Big Bang wasn't a void or a vacuum or a bounce. It was another universe slamming into ours. But that raises a horrifying question. If brane collisions happen, can they leave scars? And numerical relativity says yes, in the form of gravitational waves. Not short, sharp merger waves like black holes create, but ultra-long wavelength space-time ripples that predate the Big Bang's expansion. Some of the new simulations show that if a bounce or brane collision occurred, those waves could survive inflation, stretched across the entire observable cosmos. And if they exist, the next generation of detectors could hear them. Gravitational echoes from a universe older than ours. But then, something breaks again. Because quantum fluctuations complicate everything. In bounce models, tiny quantum ripples don't vanish at the bounce. They evolve through it. They get squeezed, distorted, rotated. And when the universe expands again, those altered fluctuations seed galaxies. That means the arrangement of galaxies today, clusters, filaments, voids, might contain fingerprints from before the Big Bang. Unless a different model is right. Because when physicists compare these theories, bounces, brane collisions, string vacua transitions, each predicts a different spectrum of fluctuations, a different anisotropy pattern, a different set of gravitational signatures. Numerical relativity has become the battleground for testing them. Not philosophically, computationally. But nothing is stable yet, because exotic matter suddenly enters the story. Some pre-bang models require matter with negative pressure or exotic equations of state. Components that can stabilize a contracting universe, drive a bounce, or trigger inflation. These aren't science fiction ingredients. They come from legitimate quantum field theory. But they behave in ways that violate normal intuition. High pressure that acts like negative gravity. Energy densities that remain constant as space shrinks. Fields that don't dilute under contraction. But that introduces a new crisis. High energy particle fields behave unpredictably near Planck densities. The Higgs field, the inflaton, and hypothetical scalar fields may undergo violent oscillations, metastable transitions, or vacuum instabilities. If any of these transitions misfire during contraction, the bounce fails. If they misfire after expansion, inflation fails. Cosmology becomes a tightrope of stability, with the universe only surviving under narrow physical conditions. And then the anisotropy problem detonates everything again. For decades, cosmologists believed that any contracting universe with even slight anisotropy would collapse into a chaotic, cigar-shaped mess instead of bouncing. But modern simulations show the opposite. Many anisotropic universes actually survive contraction, reorganize their energy, and pass cleanly through the bounce. Some even transition into inflation more smoothly than perfectly symmetric universes do. That single discovery overturns 40 years of assumptions. But the chaos escalates again when physicists realize that these same extreme curvature regimes appear in black hole interiors. The numerical techniques used to simulate black hole mergers, the very algorithms that caught gravitational waves for the first time, can be turned backward onto cosmology. The tools used to model collapsing horizons now model the pre-bang universe. Black hole physics and early universe physics merge into one discipline. But even this unification cracks open a new problem. How does the pre-bang state transition into inflation smoothly? You can't just jump from a contracting universe to exponential expansion. The equations have to connect. And the new simulations show that under certain conditions, precise conditions, the universe's curvature and energy fields naturally transition into the inflationary regime. No singularity, no break, just a continuous evolution from pre-bang to post-bang. Unless the observational data murders that idea. Because if a pre-bang era existed, it must leave marks in the cosmic microwave background. Cold spots, anisotropy alignments, subtle irregularities. Some anomalies already exist. They're small, not definitive, but hauntingly consistent with certain bounce signatures. Unless it's quantum tunneling. Some models don't predict a bounce or a collision. They predict a tunneling event, a universe emerging from a prior vacuum through a quantum fluctuation. The pre-bang state would be a metastable vacuum, not a universe. A place with no classical space or time, just fields fluctuating until one fluctuation tunnels into a new expanding space-time. That space-time is ours. But that version collapses when you introduce time reversal symmetry models. These models propose that the universe before the Big Bang was a mirror universe, obeying the same laws but running in reverse. Entropy decreasing, time flowing the opposite way, not mystically, mathematically. And these models also eliminate the singularity. And finally, the stakes get impossibly higher when physicists attempt the full timeline reconstruction. Pre-bang state, bounce or transition, inflation, reheating, Big Bang nucleosynthesis, recombination, cosmic structure formation, modern universe. The chain is continuous, no gaps, no singularity, no beginning in the traditional sense. And numerical relativity is the only reason this reconstruction is possible. The moment you try to stitch all these pre-bang scenarios into one coherent timeline, everything destabilizes again. Because the models refuse to agree on what the universe was doing 1 Planck time before the bounce. That's 10 to the minus 43 seconds. An interval so small even quantum gravity strains to describe it. Yet every breakthrough simulation keeps circling back to this moment. Because what happens there determines whether the universe bounces, tunnels, collides, or simply transitions. And here's where the crisis detonates. Different initial conditions that look nearly identical evolve into radically different outcomes. Tiny differences in curvature gradients, differences as small as 10 to the minus 80, explode into entirely different universes. Some inflate, some collapse, some shear into directional chaos, some tunnel out of existence. And then it gets worse. Because the new non-homogeneous simulations show that if the universe is slightly lumpy before the bounce, inflation is more likely to ignite after the bounce. That shouldn't happen. Smooth universes should inflate more easily. But the data coming out of high-resolution numerical relativity grids shows the opposite. Asymmetry stabilizes inflation. Irregularity is fuel. Smoothness is fragile. The early universe wasn't a clean slate. It was a minefield where only the messiest initial conditions survive. But that creates a bigger contradiction. If messy, clumpy universes inflate more easily, then maybe inflation wasn't triggered by a field at all. Maybe it was a geometric consequence of an irregular pre-bang state. That idea terrifies theorists because it means quantum gravity, not particle physics, drove inflation. And if that's true, the inflaton field might not exist. The field responsible for the universe's rapid expansion might be a mathematical convenience, a placeholder for something deeper. But this is where string theory cuts in, slicing open the conversation. Because in certain pre-Big Bang string models, the early universe doesn't need an inflaton. Instead, it's driven by dilaton fields or moduli fields, exotic string theoretic components that determine the shape of extra dimensions. When these dimensions shift shape, energy density spikes, and that spike can drive a massive expansion. Inflation becomes a dimensional transition, not a field-driven burst, unless the brane collision models are right. Then, inflation is simply the aftershock of a universe-sized impact event. The branes collide, the energy surges, the universe expands, and inflation is a recoil wave. But the simulations that model these collisions keep uncovering something terrifying. The angle of the collision matters. If the branes collide at a slight tilt, a tilt as small as 10 to the minus 6 radians, they produce characteristic directional anisotropies in the distribution of density fluctuations. That's a measurable signature. A signature that shouldn't exist if the universe's primordial fluctuations were purely random. And here's where everything spirals into a new crisis. Some of those directional signatures appear in the CMB anomalies, the same anomalies that standard cosmology struggles to explain. Cold spots, axis alignments, parity violations, statistical weirdness in the largest angular modes, none definitive, all unsettling, all potentially pointing to an event before the Big Bang. Unless it's gravitational waves. Because if a prior universe collapsed and bounced, the contraction phase would generate gravitational waves. Massive, ultra-long wavelength gravitational waves. Ones so stretched that their wavelengths exceed the size of the observable universe. These waves wouldn't appear as oscillations. They'd appear as distortions in the statistical structure of density fluctuations. And some anomalies in the CMB power spectrum look eerily like such distortions. But none of this works if quantum fluctuations die at the bounce. And they don't. Modern quantum cosmology shows that fluctuations survive the bounce, but get squeezed, the exact technical term, which amplifies certain wavelengths and suppresses others. This squeezing effect makes the pre-bang universe visible today in the large-scale structure of galaxies, unless the singularity is real. Except it can't be. Because high-precision modeling eliminates it. The singularity, the infinite density point, only appears when equations assume perfect smoothness. Remove the symmetry assumption, and Einstein's field equations no longer produce infinities. They produce turnarounds, plateaus, transitions, but never true divergences. And the moment singularities disappear, time has no beginning. But then comes the collapse, because even if singularities vanish, not every theory predicts a prior universe. Some predict a pre-Big Bang vacuum state, a kind of empty proto-reality with no classical space-time, just quantum fields fluctuating in a timeless foam. But that foam is unstable. The lowest energy vacuum can tunnel into a space-time bubble, and that bubble becomes a universe. That bubble becomes ours. The Big Bang is the inflating boundary of that bubble, unless time reversal symmetry takes over. Then, the pre-bang universe is a mirror universe, where time flows backward, entropy decreases, and physics remains perfectly lawful. This isn't philosophy. It's a consequence of CP to symmetry applied to cosmology. the math works disturbingly well. Too well. Because if the universe is time-symmetric across the bounce, then the arrow of time is emergent, not fundamental, a thermodynamic illusion. But that brings us to the most violent pivot yet, exotic matter. Because contraction doesn't stop itself. Something has to counteract it. That something is exotic matter with negative pressure, components that gravitationally repel rather than attract. Dark energy is one example, but there are more exotic ones predicted by quantum field theory. Ghost, condensates, Galilean fields, phantom energy with equations of state below UO equals -1. These components can stabilize contraction and produce a bounce. But they're unstable. One wrong fluctuation, and they tear space-time apart before a bounce can form. Unless loop quantum gravity is correct, then exotic matter isn't needed. Repulsive gravity emerges naturally from quantum geometry. Contraction hits a minimum scale. Curvature hits a maximum value. And then the universe rebounds like a compressed spring. But here's where black hole physics crashes into the conversation again. Black hole interiors may undergo the same bounce. Some loop gravity simulations suggest that when a black hole collapses past a certain density, quantum repulsion halts the collapse and rebounds the core into a new expanding region of spacetime. A baby universe, connected through the black hole interior. If true, black holes aren't endpoints. They're cosmic reproduction mechanisms, and the Big Bang was simply the bounce interior of a parent universe's black hole. Unless string theory is right, and black holes smear into fuzzballs with no singularity whatsoever. But fuzzballs also eliminate the singularity behind the Big Bang. Another mechanism. Same conclusion. No beginning. And then, abruptly, the crisis shifts again. Because now you have to connect all of these pre-bang possibilities to actual observations. And the only way to do that is through the cosmic microwave background. It contains fingerprints, patterns, angular power distortions, low multi-pole anomalies, hemispherical asymmetry, cold spots, alignments. And every one of these features could be a remnant of a pre-bang universe. Unless they're just statistical noise. Unless they're cosmic variants. Unless they're signals. Next comes the gravitational wave detectors. LISA, DTGO, BBO, Cosmic Explorer. These instruments will push sensitivity to wavelengths long enough to detect pre-bang relics. If the universe bounced, there will be a specific spectrum, a rising profile at low frequencies. If brane collisions happened, the spectrum will be jagged with directional signatures. If tunneling occurred, the waves will be nearly absent. If a prior universe collapsed, the spectrum will contain a cutoff. These are concrete predictions. The detectors will choose between them. But before that decision arrives, cosmologists are already confronting the deepest contradiction. Every model predicts something different, yet every model can reproduce the universe we see today. They all converge on the same macro-universe: galaxies, stars, voids, filaments, but diverge catastrophically in the pre-bang era. Unless something deeper unifies them. And that something may be the full timeline reconstruction, the attempt to combine quantum gravity, numerical relativity, and observational cosmology into one continuous chain of events that extends backward past the Big Bang and forward into cosmic heat death. A chain with no break, no beginning, no singularity. But the chain only forms if we can resolve the final paradox. What state did the universe have immediately before the bounce, before the collision, before the transition, before the tunneling? Numerical relativity simulations keep pushing the boundary closer, shrinking the unknown region. But the region never fully disappears, not yet, and the universe is running out of places to hide. The timeline is forming. The pieces are aligning, but the picture is not finished. The moment we press deeper into the pre-bang timeline, everything becomes unstable again, because the models that seemed promising a few minutes ago suddenly refuse to agree on one catastrophic detail: how close the universe actually got to maximum curvature before reversing direction. That single parameter, the curvature peak, decides whether the pre-bang universe was smooth, chaotic, fragmented, cyclic, quantum granular, or teetering on the edge of gravitational collapse. And the new simulations reveal something unthinkable. The curvature peak might not be universal. It might depend on the very fluctuations it produces. This breaks every intuition in cosmology. We expect the rules to be the rules, fixed, rigid, absolute. But as the simulations scale toward Planck curvature, the rules start bending. Curvature affects fluctuations. Fluctuations affect curvature. The bounce threshold becomes a feedback loop. Some universes bounce earlier, some later, some almost never bounce at all. But that creates a deeper panic. If contraction does not hit a single, well-defined bounce scale, then the pre-bang universe wasn't governed by a single law. It was governed by competing effects, each amplifying the other. Inflation could ignite too early, too late, or, in some simulations, never ignite at all, resulting in tiny trapped universes that never grow large enough to produce galaxies. And here's where multiple models suddenly start overlapping in a way nobody predicted. Loop quantum cosmology predicts a bounce because space-time becomes discrete and repulsive at high density. String cosmology predicts a bounce because the duality symmetry forbids infinite curvature. Brane cosmology predicts a bounce because collisions cannot produce infinite energies in higher dimensions. GR-based numerical relativity predicts a bounce because nonlinear curvature terms create a turnaround before singularity. 4 totally different mechanisms. One identical outcome. Either that's a coincidence of cosmic proportions, or the universe is screaming at us that the singularity never existed. But even if all roads lead to a bounce, the nature of that bounce remains violently disputed. Some simulations show a sharp rebound. The universe collapses, hits a minimum volume, and ricochets outward at extreme energy density. Others show a soft bounce, a gentle transition where contraction slows, halts, and reverses without any violent spike. And some show oscillatory bounces. The universe expands, contracts, expands, contracts, each cycle longer than the previous one. But then the rhythm shatters when exotic matter enters again. Because if even a tiny amount of exotic negative pressure matter exists, it can freeze the contraction before it ever reaches quantum scales. That means the bounce could happen at densities far below what quantum gravity predicts. It could be caused by fields we already know exist: scalar fields, ghost fields, inflaton-like potentials, modified Higgs dynamics. These familiar ingredients can freeze contraction under the right conditions, unless those fields destabilize. And some simulations show exactly that. Small instabilities in exotic fields amplify during contraction, producing curvature spikes that fragment space-time into nearly disconnected regions. Universes that begin unified split into sectors with wildly different densities. Some bounce, some crunch, some collapse into high curvature filaments resembling interior black hole singularities. Except black hole singularities don't exist either. Not in modern quantum gravity. In loop gravity, they bounce. In string theory, they fuzz. In modified gravity, they smear, meaning the same mechanisms protecting the early universe from singularity protect black holes too. That connection may not be a coincidence. It may be the entire point. The Big Bang was not a special event. It was a large-scale version of something happening inside every black hole. Unless that's wrong. Because the simulations that convert black hole interior dynamics into cosmological dynamics rely on assumptions about symmetry that might not hold for the universe. Remove those assumptions and the black hole interior becomes violent, anisotropic, unstable, multidirectional. The bounce becomes unpredictable. The structure becomes fragmented. And the same issue reappears in cosmology. Remove symmetry, and pre-bang conditions become chaotic. But here's the shocking part. Despite the chaos, many simulations produce the same post-bang universe we live in. Smooth, flat, isotropic, with the same spectrum of density fluctuations, with the same potential to ignite inflation, with the same conditions for Big Bang nucleosynthesis. Somehow, the chaos gets erased. Unless inflation erases it. Inflation smooths everything to near-perfect uniformity. It wipes out curvature, anisotropy, gradients, irregularities, quantum wrinkles, everything. Which means the pre-bang state could have been unbelievably messy, and inflation would hide the evidence. Unless inflation never happened. Because some bounce models replace inflation entirely. They don't need a rapid exponential expansion after the bounce. The bounce itself produces the right initial conditions. These are called matter bounce cosmologies, and they predict different patterns of gravitational waves, different tilts in the fluctuation spectrum, different shapes in the CMB. Patterns that future observations can measure. But here's the crisis. Some CMB anomalies match the predictions of bounce cosmologies better than inflationary ones. Not all of them, not conclusively, but enough to spark a scientific brawl between two camps, the inflationists and the bouncers. The inflationists point to decades of successful predictions. The bouncers point to unexplained anomalies and mathematical elegance. Both sides cite simulations. Both sides claim victory. Neither can yet prove it. And then, everything spirals downward again when we confront the most dangerous idea in the entire pre-bang narrative: non-homogeneous initial conditions. Because when you allow the early universe to be clumpy, uneven, and wildly irregular, you open a Pandora's box of possibilities. Universes that expand only in certain directions. Universes that form large-scale anisotropies. Universes that cycle between expansion and contraction along different axes. Universes that fragment into multidimensional pockets. Universes with gravitational turbulence that never dies. And yet, some of these chaotic universes still evolve into a clean, smooth, nearly perfect universe like ours. The key is the evolution through the bounce. Some anisotropies decay, others survive, others convert into scalar fluctuations. And numerical relativity shows that certain chaotic pre-bang universes naturally produce the exact density fluctuation spectrum needed to form galaxies billions of years later. Unless the pre-bang state tunnels into our universe instead of bouncing. Then, the initial conditions are not inherited from a prior universe at all. They are generated by quantum tunneling itself. That produces different signatures, different fluctuation distributions, different gravitational wave spectra, unless it's the mirror universe version. Then, time flows backward before the Big Bang. Entropy decreases, equations remain invariant, and the Big Bang is simply the moment where both arrows of time diverge. one forward, one backward. In that scenario, the pre-bang universe is smooth, not chaotic. Time reversal symmetry enforces it, and the fluctuations we see today emerge from vacuum fluctuations, not from a prior universe's structure. Unless numerical relativity proves otherwise, and it might. Because when simulations sneak into the Planck regime, time symmetry breaks unless extra fields stabilize the system, unless those fields don't exist. And the deeper we push, the more every theory starts eating itself. But we still haven't confronted the biggest paradox. How do we extract observational evidence for something that happened before space-time as we know it existed? The answer breaks open through gravitational waves, and right here, the video pivots again. Because if the pre-bang universe existed, it must have produced gravitational waves. Massive ones, long wavelength ones. Some models predict a sharp spectral spike at ultra-low frequencies. Others predict a soft rise. Others predict directional modulation. Brane collisions predict imbalance. Bounces predict symmetric spikes. Tunneling events predict near silence. If any of these signatures are real, Lisa will see them. And if Lisa sees them, every pre-bang model that doesn't match gets annihilated. But then comes the horror. The absence of detection doesn't rule out a pre-bang universe. It might just mean inflation erased the evidence, or the bounce smoothed it, or the transition absorbed it, or the early universe never produced waves in measurable quantities, which means gravitational waves could either expose the truth of the pre-bang universe or bury it forever. And now the final escalation begins. Because the full timeline reconstruction is underway, cosmologists are threading the models into one continuous chain. Pre-bang state, contraction, quantum or exotic freeze, bounce or transition, inflation or no inflation, reheating, Big Bang physics, nucleosynthesis, recombination, galaxy formation, large-scale structure. 1. Continuous story. No singularity, no beginning, no edge. But the story is not complete until we lock down the pre-bang state. And that is the last missing piece. The deeper the simulations push into the pre-bang era, the more violently the timeline unravels, because now the models begin contradicting not just each other, but themselves. You take the same equations, the same initial conditions, the same energy densities, run them at higher numerical precision, and the pre-bang universe mutates, not randomly, systematically. Increasing resolution reveals new instabilities. Corrections that were invisible at coarse grid scales explode at finer ones. Fields that behaved smoothly suddenly oscillate. Curvature plateaus become spikes. Bounces split into multi-stage rebounds. This means the universe wasn't fine-tuned. It was sensitive. And sensitivity at this scale is terrifying. Because if tiny quantum corrections change the entire fate of a universe, then the pre-bang era wasn't a calm prelude. It was a razor's edge where the cosmos could have become anything. A void, a crunch, a fractal web, a directional collapse, or a universe we would never recognize. But here's the disturbing twist numerical relativity keeps uncovering. Despite the chaos, certain attractor states keep reappearing. No matter how irregular the pre-bang universe becomes, no matter how many fields you perturb, no matter how many anisotropies you introduce, the simulations keep drifting toward a handful of stable, pre-bang configurations. These are called cosmic attractors, and they may be the real origin of the universe. But the moment that idea stabilizes, brane cosmology destabilizes it again. Because in the brane picture, The pre-bang state is not an attractor. It's a trajectory, a universe-sized membrane moving through higher dimensional space, interacting with other branes through potentials we barely understand. And these interactions create energy spikes, tension gradients, warping of extra dimensions, all of which can trigger a brane collision. But the nightmare begins when you try to simulate these interactions in full numerical relativity. Gravity behaves like a wild animal in higher dimensions. Waves reflect off boundaries. Shock fronts curve. Branes warp and twist like cosmic sheets in a windstorm. The simulations reveal collisions that are smooth and collisions that shred space-time. And in the violent ones, the Big Bang looks nothing like the beautiful thermal bath described in textbooks. It looks like a rupture. Unless string theory pre-bang models are right, then the universe doesn't start from rupture at all, but from a dilaton-driven contraction phase. As the dilaton field grows, the extra dimensions stretch, the universe contracts in three-dimensional space, and the entire pre-bang cosmos becomes a giant energy reservoir waiting for release. When the release happens, the string phase transition, space-time erupts outward. But that raises a monstrous question. How long was the pre-bang era? If it was a contracting universe, millions of years, billions, trillions? If it was a vacuum state, was it eternal? If it was a brane motion, could it have lasted longer than our entire observable universe's lifespan? We don't know. And the simulations can only push so far back before quantum gravity takes over and classical relativity collapses. So we pivot. Again. Because loop quantum cosmology is the one framework where the pre-bang timeline is mathematically trackable all the way through the bounce. And what it reveals is brutal. The universe before the Big Bang had its own arrow of time, its own increasing entropy, its own causal structure, its own cosmic evolution. The Big Bang is not the beginning. It's a bridge, a bottleneck, a minimum volume through which two arrows of time pass like traffic in opposite directions. Unless the mirror universe interpretation is correct, then there aren't two arrows of time flowing away from the bounce. There's one arrow mirrored. The pre-bang universe is our universe reversed, time inverted, entropy decreasing instead of increasing. Everything that moves forward on our side moves backward on the other. This is not science fiction. It's the direct consequence of CPT symmetry. If you reverse charge, parity, and time, the laws of physics remain unchanged, which forces a terrifying thought. Somewhere before our Big Bang, an entire universe might have existed, identical to ours, but running in reverse time, and we will never meet it. Unless gravitational waves from the bounce preserve its memory. Because if the bounce was time-symmetric, then waves from the contracting phase could propagate into the expanding phase. The shape of those waves, their power spectrum, their polarization, their amplitude, would encode the history of the reverse-time universe. And that's where DESIGO, LISA, and the Einstein telescope come in. These detectors are sensitive to frequencies low enough, long enough, wide enough to extract pre-bang signatures embedded in the gravitational background. If a bounce happened, we should see a blue-tilted spectrum at ultra-low frequencies. If a brane collision happened, we should see directional polarization. If quantum tunneling happened, we should see a suppressed spectrum. If a cyclic universe existed, we should see repeating imprints, echoes of universes long dead, unless inflation wiped everything clean. And inflation might have been merciless, because in standard inflation, the universe expands by a factor of 60 or more, 10 to the 40 times in size, stretching any pre-existing gravitational waves to absurd wavelengths. diluting them to unobservable amplitudes. Inflation is a cosmic eraser, scrubbing away everything except its own imprint. The pre-bang universe could have screamed into space-time, and inflation would have buried it, unless inflation didn't happen. Unless the bounce itself replaced it, unless cosmic attractors replaced it, unless exotic matter replaced it, unless string geometry replaced it. The models oscillate violently between these possibilities, but then the crisis jumps again. Because now we turn to quantum fluctuations. Every universe model must answer one question. Where did structure come from? Galaxies, clusters, voids, filaments, superclusters, supervoids. The entire cosmic web. In inflation, tiny quantum fluctuations get magnified to cosmic scale. But in bounce cosmologies, fluctuations evolve through contraction, get squeezed by the bounce, and emerge with the same statistical properties inflation predicts, without needing inflation itself. Except the squeezing process predicts extra correlations, subtle non-Gaussianities, extra structures, slight directional modes, and we're starting to see hints of exactly that. Faint whispers buried in the cosmic microwave background. Patterns inflation struggles to explain, but bounce models love. Unless those patterns are noise, unless they're artifacts, unless they're signals we aren't ready to decode. And then everything snaps back to numerical relativity, because it is the only tool powerful enough to test these scenarios on the scale they demand. Relativity simulations solve Einstein's equations at millions of grid points, tracking curvature, matter fields, quantum corrections, higher dimensional warping. They model collapse, bounce, transition, and explosive expansion. They test whether black hole tools can apply to cosmology. And terrifyingly often, they say yes. Black hole approaches survive in cosmology. Horizon formation appears. Trapped surfaces appear. Apparent horizons form in contracting universes, only to evaporate after the bounce. Space-time pinches, space-time unpinches. Universes behave like interior singularity analogues, only without the singularity. But then, pre-bang anisotropies kick the door open again. Even small directional differences, shear, tilt, curvature distortion, can change the fate of the universe during contraction. Too much anisotropy and the universe collapses into a BKL, Belinsky-Kalatnikov-Lifshitz chaotic state. Too little, and it bounces symmetrically. Right in between, simulations show something shocking. Universes that form directional scars, long-lasting anisotropic imprints that survive the bounce and leak into the post-Big Bang cosmos. These imprints would appear today as subtle anomalies in cosmological data. And we see anomalies. Cold spots, strange alignments, statistical tensions. Not conclusive, not definitive, but too consistent to ignore, unless they're coincidence, unless cosmology is tricking us, unless the pre-bang world is speaking through noise. But the timeline continues, because the final task, the impossible task, is to assemble a complete cosmic sequence from pre-bang physics all the way to modern structure. A chain that doesn't break, a chain with no singularity, a chain that unites quantum gravity with astrophysics. And that reconstruction is underway. But the deepest revelations haven't arrived yet, because next comes the collapse of classical space-time itself. The collapse of classical space-time begins the moment we ask the most forbidden question in all of cosmology. What was the geometry of the universe one instant before the bounce? Every. Theory claims to know. Every simulation claims to approximate it, and every one of them collapses under higher resolution. Because at ultra-high curvature, space-time does something no classical equation can tolerate. It stops behaving like a smooth surface. It fractures. Not violently, not physically tearing, but computationally. Curvature gradients steepen so abruptly that the grid resolution required to capture them skyrockets beyond anything achievable with current computing power. The simulations begin to flicker. Numerical instabilities appear. The equations start oscillating. And that instability is telling us something profound. Classical spacetime cannot describe the pre-bang universe, but quantum spacetime can. Except quantum spacetime isn't spacetime at all. In loop quantum cosmology, spacetime dissolves into discrete geometric atoms. In string theory, spacetime becomes a holographic projection of vibrating strings. In brane models, spacetime is a membrane floating in higher dimensions. In asymptotic safety, spacetime flows into a fixed, ultraviolet point. 4 frameworks, 4 different ontologies. None of them give the same answer to what spacetime is under Planck curvature. And this triggers the next explosion. The geometry of the pre-bang universe might not even be 4-dimensional. Some simulations of string cosmology suggest the early universe oscillated between different effective dimensionalities. 3 large dimensions before the bounce, 2 small dimensions after the bounce 9 after, then 3 again. The Big Bang wasn't an explosion. It was a dimensional reconfiguration. Unless brane cosmology is right, and the pre-bang geometry was higher dimensional all along, 5, 6, or even more dimensions, compressed by brane tension until collision. When the branes collide, the extra dimensions warp, dump their stored energy into our dimensions, and vanish or compactify. Unless loop gravity is right, and dimensionality stops being meaningful at that scale because the underlying quantum geometry is non-differentiable. No smooth directions, only combinatorial structures. Unless asymptotic safety is right, and the geometry flows toward fractal-like behavior at high energies, with dimension dropping to 2 at the Planck scale. This is the kind of theoretical violence happening behind the Big Bang. But here's where the chaos becomes unbearable. Despite having totally different microscopic descriptions of spacetime, all these theories can produce a bounce. The mathematics differ, the mechanism differs, the physics differs, but the outcome, no singularity, is the same. Whatever spacetime is, it doesn't allow infinities, and that overturns the deepest assumption cosmology ever held. But this is only the beginning of the collapse. Because when spacetime destabilizes, matter destabilizes with it. Fields oscillate, vacuum states shift, energy densities jitter. The Higgs field, which normally sits in a calm potential well, begins to fluctuate violently at densities near the bounce. These fluctuations can trigger vacuum decay. Not catastrophic for the universe, catastrophic for the simulations. Because vacuum decay would prevent the bounce entirely. Yet the bounce happens, which implies the Higgs field must be anchored by corrections we haven't discovered. Higgs stabilization models explode into the literature. Higher order operators, non-minimal couplings, gravitational anchoring, all to keep the Higgs from destroying the universe before the Big Bang. Unless the Higgs wasn't stable, unless it did fluctuate, and the fluctuations passed through the bounce as enhanced quantum perturbations, the seeds of galaxies today. This idea terrifies cosmologists because the fluctuation spectrum would be almost indistinguishable from inflationary predictions, meaning the entire cosmic structure we see today could be the fossilized echo of Higgs instability in a pre-bang universe. But then exotic matter storms back into the conversation. Negative pressure energy components, phantom fields, quantum fields. They can stabilize the contracting phase, slow the collapse, and ensure the bounce occurs at a non-catastrophic density. But these fields are unstable. They can blow up. They can produce runaway expansion before the bounce. They can eliminate the bounce entirely. Only certain equations of state, very narrow ones, produce a safe contracting to bouncing transition. If the universe drifted even slightly outside that range 14 billion years ago, the bounce would never have happened. And this is where numerical relativity becomes savage. Because when you push these models through the equations with full non-linear corrections, most initial conditions die. They crunch, they collapse, they shear apart. Only a tiny fraction survive. The universe that produced us was rare, not cosmically privileged, cosmically improbable. Unless cosmic attractors rescue us again. Because the same simulations that show most initial conditions die also show a stunning phenomenon. The surviving universes converge toward the same final state before the bounce. Chaotic at first, eventually smooth, directional at first, eventually isotropic, fragmented at first, eventually unified. The pre-bang universe had attractors, gravitational structures that pulled all possible universes into similar configurations before the bounce. Cosmic selection, not anthropic, dynamical. The laws of gravity choose which universes live long enough to bounce. And that choice might explain why our universe looks the way it does today, unless brane cosmology slams through the wall again. Because brane collision models don't need attractors, they produce the Big Bang through higher dimensional dynamics, not through contraction in our dimensions. If branes collided, the universe before the collision could have been wildly chaotic. Higher dimensional shape fluctuations, brane curvature waves, warping, twisting, folding. A pre-bang ocean of multi-dimensional turbulence. And that turbulence would imprint on the collision event, which means our universe contains fingerprints from a higher dimensional impact scar. Unless inflation erased them. Unless it didn't. Because some of the CMB's strangest anomalies line up suspiciously well with predictions from brane collision impact waves. Directional asymmetries, power suppression at low multipoles, the so-called axis of evil, patterns that inflation has trouble explaining. Unless they're noise, unless they're clues, unless the pre-bang universe has been staring us in the face since 2003. But now the script pivots again, violently, into the quantum realm. Because the collapse of classical spacetime forces us to look at quantum tunneling models. And in those models, the universe didn't bounce. It materialized. It tunneled. It leaped from a metastable vacuum into an inflating universe. No contraction, no prior universe, just a quantum event. But that event leaves scars in the CMB too. Extremely low tensor modes, nearly perfect Gaussian fluctuations, a specific ratio of scalar amplitudes, and a suppressed large-scale power spectrum. And we see hints of that too, not conclusively, not decisively, but enough to keep tunneling models alive. Unless cyclic cosmology is right, then the universe didn't tunnel, didn't bounce once, didn't even start. It cycles, expands, contracts, expands, contracts. Forever. The Big Bang is just the last bounce in an eternal chain. Unless the cycles grow longer each time. Unless entropy builds too fast. Unless exotic matter decays. Unless the cycles break. Unless... But this is where time reversal symmetry enters again and detonates everything. Because if the universe is time-symmetric across the bounce, then the Big Bang is not a birth, it's a midpoint. And the pre-Bang universe, the one before ours, wasn't just before, it was reverse. Its entropy decreases as it moves toward the bounce. Ours increases moving away from it, 2 time arrows, one shared space-time throat, unless quantum gravity breaks that symmetry too. And the worst part? We don't know yet. Which brings us to the edge of the greatest crisis in modern cosmology: observational tests. Because if any of these pre-Bang models is correct, we should see subtle patterns in the cosmic microwave background. Suppressed low multipoles, hemispherical power asymmetry, alignment of quadrupole and octupole, anomalies in temperature gradients, hints of non-Gaussian correlations, signatures of anisotropic contraction, relic gravitational wave tilt, pre-inflationary imprints, and we see all of them. But none are definitive. None reach the gold standard confidence threshold. None prove a pre-Bang universe. But none can be ignored. Numerical relativity is tightening the noose. Quantum gravity is closing the gaps. Observations are whispering. Gravitational waves are coming. The timeline is forming. But one category of evidence remains untouched, and it is the most dangerous of all. The most dangerous evidence isn't gravitational waves or CMB anomalies or exotic matter signatures. It's something far simpler and far harder to escape: the universe's large-scale structure. Because galaxies are not sprinkled randomly across space. They form filaments, sheets, nodes, clusters, and voids so enormous they defy probability. And here's where the pre-Bang universe lunges out of hiding. The distribution of these structures contains information that inflation alone struggles to erase. Inflation wipes away curvature. It wipes away anisotropies. It wipes away relic gravitational signatures. But what it can't fully erase are correlations, patterns, statistical relationships baked into the primordial fluctuations before inflation even starts. And now comes the twist that cosmologists did not want to face. Some of those correlations match pre-bounce predictions better than inflationary predictions. This is not wishful thinking. It is statistical revolt. Large-scale structure surveys reveal features that inflation smooths too well: slight alignments, anisotropic correlations, unexpected clustering modes, a faint but persistent excess of power at certain scales, a missing deficit at others. Pattern mismatches inflation tries to blame on cosmic variance, but the probability keeps shrinking. Every new dataset makes the anomalies louder, unless they're noise, unless they're artifacts, unless they're the echo of a universe that came before ours. But the moment that possibility gains momentum, the next crisis detonates. Because large-scale structure doesn't just tell us the universe might have had a pre-Bang phase, it tells us what kind of phase it was. And that is catastrophic for several beloved theories. Chaotic pre-collapse universes leave a particular spectral tilt. Dimensional transitions leave directional modulations. Brane collisions leave gradient scars. Matter bounce models leave characteristic oscillations in the power spectrum. Quantum tunneling models leave near-perfect Gaussian distributions. Time-symmetric bounces leave symmetric correlation patterns across scales. Now the simulations get ruthless. Feed all these predictions into the cosmic structure data, and most pre-Bang scenarios die instantly. Their predictions don't match. They produce structures too clumpy, or too smooth, or too directional, or too isotropic, or with the wrong amplitude. Whole classes of theories vanish overnight, But the survivors? They align disturbingly well with the same handful of models that survived the earlier stages of the script. Loop quantum, cosmology bounces, ekpyrotic brane collisions, asymptotically safe bounces, time-symmetric bounces, certain string pre-bang transitions, 5 frameworks, 5 radically different mechanisms, one identical conclusion: something existed before the Big Bang. Unless inflation wipes the slate, unless quantum noise corrupts correlations, unless our measurements are biased, unless... But before that thought resolves, the entire cosmological framework ruptures again. Because now we confront the most explosive piece of evidence: the shape of the power spectrum itself. Inflation predicts a nearly scale-invariant spectrum, almost flat, almost perfect, almost boring. But the data shows subtle wiggles, oscillations, features. These wiggles are too structured to be noise, too weak to be a discovery, but too persistent to ignore. And several pre-bang models generate exactly those wiggles when quantum fluctuations pass through the bounce. The universe might be humming a memory. Unless inflation is correct, and the wiggles come from a transient feature in the inflaton potential. Unless they come from particle production. Unless they come from a decaying mode. But the more simulations refine the pre-bang models, the more the wiggles match bounce predictions. It's not proof, it's not victory, but it is a direction. And then everything accelerates again, violently, because now we must confront the most catastrophic prediction of pre-bang cosmology. Our universe is not unique. In bounce models, universes branch. In brane models, collisions repeat. In cyclic models, history recycles. In tunneling models, multiverse bubbles inflate endlessly. In time-symmetric models, universes come in pairs. If the pre-bang state existed, then our universe is one of many. Unless quantum gravity enforces uniqueness, unless the attractor state funnels all universes into one path, unless the bounce erases memory so thoroughly that only one universe emerges. But the moment we attempt to answer this, the mathematics attacks us again. Because uniqueness depends on the nature of the bounce, and the nature of the bounce depends on exotic matter, and exotic matter depends on the vacuum, and the vacuum depends on quantum fields, and quantum fields depend on curvature, and curvature depends on the bounce. It's circular, it's recursive, it's self-referential. The pre-bang universe is a paradox factory, but we're not done. We haven't even entered the most dangerous territory yet, because the final battleground, the one that threatens to annihilate half the theories on the table, is gravitational entropy. The entropy problem is a knife at the throat of every cosmological model. Entropy always increases, always. So how can the universe contract, collapse, compress, and then bounce without violating thermodynamics? Inflation cheats. It resets entropy density by expanding space faster than matter can thermalize. Brane collisions cheat. Entropy flows into extra dimensions during contraction. Loop cosmology cheats. Entropy decreases as quantum geometry compresses the universe. Time-symmetric models cheat. Entropy decreases only in the pre-bang universe, not in ours. Matter bounce models cheat. Entropy is diluted by the bounce. Each model has an escape hatch. Each escape hatch relies on physics we haven't fully tested. And the moment numerical relativity tries to simulate entropy gradients near Planck densities, the equations explode. Energy flows reverse. Quantum corrections unpredictably flip sign. Gravitational entropy refuses to behave. Because gravitational entropy isn't a number. It's a structure, a configuration, a relationship between curvature and information. And when curvature approaches its maximum, entropy stops being definable. Unless entropy is emergent, unless time is emergent, unless causality itself is a macroscopic illusion. And we are forced to face the most terrifying possibility yet. The Big Bang wasn't the beginning, but neither was the bounce, nor the contraction, nor the pre-bang vacuum, nor the brane collision, nor the tunneling event. Because the universe might not have a beginning, it may be infinite in both directions, not cyclic, not bouncing, not repeating, just existing, in different phases, different forms, different regimes, forever. Unless the next section proves otherwise, because the next frontier is the one cosmologists fear most. What happens if the pre-bang universe left direct, measurable, unavoidable evidence, and we simply haven't recognized it yet? And that's where the video goes next. There is a possibility so alarming that cosmologists rarely say it out loud. The pre-bang universe may have left evidence so blunt, so enormous, so unavoidable, that we've been staring at it for decades without realizing what it is. Not faint signals, not whispers in the CMB, not subtle oscillations or statistical oddities. We're talking about structures so massive they break simulation after simulation. Structures the lambda CDM model struggles to justify. Structures that standard inflation tries to smooth away, but didn't. We're talking about cosmic voids. Gaps so huge they're not supposed to exist. Regions billions of light years across with almost no galaxies. Places where matter density is so low you could fit entire civilizations and never bump into a star. But here's the part cosmology textbooks don't emphasize. Some voids match the predicted scars of a pre-bounce contraction. Contracting universes generate imprint regions, pockets where matter density becomes uneven during collapse. After the bounce, those pockets expand, stretch, and inflate into massive voids. Inflation hides the details, but the gross structure, the emptiness, survives. Observations reveal voids too large for inflation to erase. Simulations show voids too large for structure formation to produce. And when researchers run pre-bang models through numerical relativity, the voids look familiar, uncomfortably familiar, unless it's coincidence, unless it's noise, unless it's our universe remembering something it shouldn't remember. But voids aren't the only colossal scars. Galactic superstructures, walls, filaments, superclusters, exhibit statistical alignments. Inflation hates. Even more disturbing? Some alignments point in the same directions as CMB anomalies, the same directions as cold spots, the same directions as polarization irregularities. If these alignments are real, and the probability that they're random keeps shrinking, then the universe might be anisotropic at the largest scales, and inflation cannot easily explain that. But a pre-bang contraction can, a brane collision can, a directional bounce can, a dimensional transition can, a cosmic shear phase can. Each of these pre-bang models naturally produces preferred directions. Axes, dominant modes. The so-called axis of evil may not be a statistical fluke. It might be a direction inherited from a universe that existed before ours, unless inflation washed it away, unless it's coincidence, unless it's cosmic variance. But the more we observe, the less variance feels like an acceptable excuse. And then everything gets worse. Because the moment we accept that large-scale structure contains pre-bang fingerprints, we must confront a brutal implication. pre-bang physics may be testable with observations happening right now. That should have been good news. Instead, it creates an existential crisis, because each model predicts a different kind of fingerprint. Bounce cosmologies, symmetric, squeezed mode enhancement, matter, bounce universes, oscillatory modulation across scales, brane collisions, directional anisotropies, plus gradient distortions, string gas cosmology, thermal fluctuation signatures, not quantum ones, cyclic universes, repeated patterns at different scales, time-symmetric universes, suppressed odd multipoles, tunneling universes, ultra-clean Gaussian perturbations. When cosmologists plug these predictions into galaxy surveys, several patterns emerge, none perfect, none decisive, but enough to destabilize the standard story, enough to whisper, "You are not the first universe." Unless these signatures result from dark matter physics, unless baryonic feedback distorts structure, unless cosmic acceleration skews interpretation. But numerical relativity simulations say something different. Some of these patterns cannot be produced by post-bang physics alone, not by dark matter, not by gravitational collapse, not by baryonic feedback, not by cosmic shear. They require something to have happened before expansion ever began. But we still haven't reached the darkest territory. Because next comes an even more monstrous clue. One hiding not in galaxies or voids, but in the Hubble tension. The Hubble tension is the growing war between the early universe's expansion rate and the late universe's expansion rate. CMB measurements predict one value. Local measurements predict a higher one. And the gap isn't shrinking, it's growing. Inflation can't fix the discrepancy. Dark energy tweaks don't fix it. Modified expansion models fight it but lose. But do you know what solves the tension effortlessly? A pre-bang contracting phase with residual modes surviving the bounce. Those modes shift the effective sound horizon. They alter the recombination physics. They tweak the initial conditions in a direction that makes both sides of the Hubble measurement correct, because the universe didn't start from a perfect, clean slate. It started with baggage. But that's not the part cosmologists fear. The part they fear is this. Not only does a pre-bang universe solve the Hubble tension, it predicts the tension. Run the simulations backward with a pre-bounce phase, and the tension emerges automatically. Run them without a pre-bounce phase, and the tension is an inexplicable anomaly. If that's true, if the Hubble tension is a pre-bang fingerprint, then the standard cosmology framework is dead. Unless the tension is measurement error. Unless new data eliminates it. Unless new physics during recombination explains it. But numerical relativity doesn't lie. A pre-bang contracting universe fits the data too well to ignore. And then the entire field detonates again, because the moment we accept a pre-bang universe, we are forced to confront how it ended. Did it collapse? Did it tunnel? Did it collide? Did it undergo a phase transition? Did it reverse time? Did it dimensional shift? Did it undergo cosmic ekpyrosis? Each answer implies a different cosmic genealogy, which means the final battle in pre-bang cosmology is not about what came before, but how it transformed into us, the transition, the bridge, the throat, the cosmic bottleneck. The moment where one universe ends and another begins. The next part of the script will enter that battle. Phase transitions, geometric collapses, quantum throat dynamics, energy transfer mechanisms, curvature reversal, entropy flow, field stabilizations. The actual machinery of going from pre-bang physics to inflation to the Big Bang, to everything. This is where the entire narrative fuses. This is where the contradictions collide. This is where the models either survive or die. This is where the pre-bang universe becomes real, and we're going straight into it. The transition, the bridge between the pre-bang universe and ours, is where every theory either succeeds spectacularly or collapses in on itself. And the horrifying truth is that the transition doesn't behave like a clean event. It behaves like a battlefield, a place where fields explode, geometries invert, entropy fluxes violently, and gravity temporarily stops knowing whether it should attract or repel. Every pre-bang model claims its own mechanism for crossing this bottleneck. But the deeper the simulations go, the more we discover that the transition is not gentle, not smooth, not elegant. It is unstable, it is violent, it is chaotically stable, meaning tiny changes in pre-bang conditions produce huge differences in the transition. Yet somehow, all pathways still land in the same post-bang universe. This paradox is the beating heart of modern cosmology. Because if universes with wildly different pre-bang properties can pass through the transition and emerge looking exactly like ours, it means the Big Bang's aftermath is a cosmic attractor, a stable equilibrium point. And attractors of that kind only form when physics is fighting itself. Now we enter the mechanisms, and each one breaks the universe in a different way. In bounce cosmologies, the transition is curvature reversal. Contraction compresses curvature until quantum geometry flips the sign of gravitational attraction. Repulsive gravity forms. The universe rebounds. But numerical relativity simulations reveal something terrifying. The reversal doesn't happen everywhere at once. It cascades. Regions hit the repulsive phase at slightly different times, generating waves, gravitational shock fronts, racing through collapsing space-time. These shock fronts ripple into the post-bang expansion, leaving subtle fingerprints in the primordial density spectrum. Unless inflation erases them, unless they survive as anomalies. In ekpyrotic brane collision models, the transition is impact. Two universes collide. The collision generates a burst of energy that seeds the hot Big Bang. But brane simulations reveal something horrifying. The collision is not uniform. Some parts impact harder than others. Some regions delay collision. This generates temperature anisotropies, directional patterns, that inflation cannot fully wash away. Observational data shows exactly those patterns at large angular scales. Unless it's statistical noise, unless it's cosmic variance, unless it's the shadow of another universe slamming into ours. In quantum tunneling models, the transition is nucleation. A tiny bubble of space-time tunnels out of a metastable vacuum. That bubble inflates into a universe. But tunneling predicts nearly perfect Gaussian fluctuations. And that is exactly what we observe. Except for the tiny, infuriating non-Gaussianities that refuse to disappear. Unless they're hints of something tunneling before tunneling. A vacuum-to-vacuum transition layered on top of a bounce. In asymptotic safety, the transition is fixed point flow. As the universe collapses, gravity becomes weaker at high energies, preventing divergence. The universe reaches a finite maximum curvature, then naturally flows into expansion. But simulations reveal a crisis. The fixed point is directional. The universe may have approached the transition anisotropically, and that anisotropy might have leaked into the CMB, unless the flow homogenizes it, unless the flow breaks, unless the fixed point doesn't exist in full non-linear gravity. In string gas cosmology, The transition is thermal. Strings in a hot, dense pre-bang environment interact, collide, stretch, and generate a universe of expanding dimensions. But the thermal fluctuations predicted by string gas models leave a very specific imprint, a slightly blue-tilted gravitational wave spectrum. Next-generation detectors might detect exactly that, unless the signal is too weak, unless inflation overwrote it, unless the universe cooled too fast. And then loop quantum cosmology crashes through the wall again, because in LQC, the transition is perfectly symmetric. The pre-bang universe approaches a minimum volume, quantum geometry kicks in, and the universe expands again as a mirror image of the contraction. But this symmetry should produce a telltale pattern, a specific modification to the primordial power spectrum at the largest scales. And we see hints of that too. Not enough to claim, not enough to dismiss. The universe is taunting us with half-truths. And just as the models begin to stabilize, everything explodes again. Because entropy enters the battlefield. Entropy is the unstoppable arrow of time. Entropy measures disorder. Entropy increases. So how does a universe go from contracting, high entropy, to bouncing, higher entropy, to expanding, even higher entropy? Without violating thermodynamics, inflation tries to hide the problem by expanding entropy density faster than entropy production. But the deeper we push the equations, the more inflation looks like an engineering fix, not a fundamental one. Bounce cosmologies claim entropy is diluted during contraction, then stretched during expansion. Brane collisions claim entropy leaks into the extra dimensions before re-entering ours. Quantum tunneling claims entropy resets during nucleation. Time-symmetric models claim entropy decreases in the reverse-time universe. But simulations show contradictions everywhere. Bounce universes accumulate too much entropy unless contraction is ultra-slow. Brane collisions dump too much entropy into the newly created universe unless the collision is fine-tuned. Tunneling universes require a metastable vacuum with impossible stability. Time-symmetric universes require perfect reflection symmetry across the bounce, something quantum chaos ruins instantly. Entropy is the assassin lurking in every pre-bang theory. And to solve it, the theories introduce something even more dangerous: entropic bridges. These are hypothetical mechanisms that allow entropy to flow from one branch of spacetime to another, from one universe to another, from pre-bang to post-bang, from contraction to expansion. The simulations propose mechanisms: exotic fields absorbing entropy, quantum geometry redistributing entropy non-locally, holographic entropy transfer across branes, entropy reversal in time symmetric models, higher dimensional entropy sinks, entropic tunneling pathways. Every one of these sounds insane. Every one comes from legitimate physics. Every one has consequences. Because if entropy can be transferred across phases of the universe, then universes can evolve. They can accumulate complexity. They can pass information forward. They can imprint memory. And then the script pivots again, sharply, because we must now confront the most catastrophic possibility numerical relativity has revealed. The pre-bang universe may have seeded our universe with information, not life, not intelligence, but structure. Patterns, modes, spectral tilts, directional correlations, statistical relics. Things inflation should have destroyed. Things quantum fluctuations shouldn't produce. Things that standard lambda CDM cannot explain. Information passed through the bottleneck, unless the bottleneck shredded it, unless inflation scrubbed it, unless we're wrong about everything. But the final crisis arrives like a gravitational shockwave. Some simulations reveal universes that survive multiple bounces, expanding, contracting, transitioning, over and over. And each bounce carries forward slightly more structure, slightly more order, slightly more entropy, slightly more complexity. This suggests something unthinkable. The universe may be learning. Not intelligently, not consciously, but dynamically, through physics alone. Evolution not of life, but of universes. Each cycle refining itself, each cycle surviving better, each cycle imprinting more structure, each cycle preparing the next, until eventually a universe arises that produces stars, galaxies, chemistry, biology, observers. Not because it was fine-tuned, not because it was designed, not because it was lucky, but because it was the outcome of billions of cosmological iterations. Unless there was only one iteration, unless we're the first, unless the next section overturns all of this. Because now we finally approach the most dangerous question in the entire script. What specific physical state came immediately before the Big Bang? Not the model, not the theory, not the category, the state. The actual configuration of the universe right before it became ours. And we are going there next. The search for the actual physical state immediately before the Big Bang is where the script stops being a chaotic landscape of possible universes and becomes a knife fight between a handful of surviving models. Because after thousands of simulations, after smashing Einstein's equations through the Planck wall, after scanning parameter spaces so huge they strain supercomputers, a small group of pre-Bang states keep reappearing, not models, not theories, not metaphysical guesses. States, concrete, physical, mathematically defined configurations of the universe that the simulations return to, again and again, no matter how violently you distort the initial conditions. And here's the terrifying part. The universe doesn't care which model you start with. Loop quantum cosmology, brane collision setups, ekpyrotic contraction, asymptotic safety flows, string gas thermalization. If you evolve them far enough back, the simulations crush everything into the same narrow handful of attractor-like structures. Almost as if the universe is funneled into them. Almost as if these states are unavoidable. Almost as if the universe is forced into them before it can become ours. But the moment we identify these states, the contradictions erupt again. Because there isn't just one. There are three survivors. Three very different pre-Bang states that refuse to die. Three configurations so stable they dominate the pre-Bang landscape. And each one leads to a different interpretation of what existed before the Big Bang. We begin with the first. 1. The ultra-slow ekpyrotic squeeze. This state appears in simulations where the universe contracts under a field with extreme negative pressure. In this scenario, the universe doesn't collapse violently. It collapses slowly. So slowly that chaotic modes die. Anisotropies flatten. Turbulence decays. Every imperfection is crushed into near non-existence. The universe becomes smooth because the contraction squeezes away disorder. The equations call this ekpyrotic smoothing. The result? A universe that approaches the bounce as a near-perfect, ultra-flat sheet of energy. This is the pre-Bang state most consistent with the lowest multipole CMB anomalies, the ones that refuse to go away. the ones that hint at a large-scale flattening before inflation ever began. Unless that smoothing didn't happen, unless the next state is closer to the truth. 2. The quantum granular high-density core. This one comes from loop quantum cosmology. Instead of smoothing, the universe becomes granular as it approaches Planck density. Space-time turns chunky, discrete, a lattice of quantum geometry. The universe doesn't flatten, it pixelates. Curvature stops increasing because quantum geometry refuses to compress further. Right before the bounce, simulations show the universe becomes a dense, homogeneous quantum crystal of space-time. And the weirdest part? Quantum fluctuations stop diverging. They stabilize. They freeze into a form that transitions smoothly through the bounce. This state predicts the exact kind of mild power suppression at large scales we observe in the CMB. Unless that suppression is coincidence. Unless the next state explains it better. 3. The anisotropic shear-dominated throat. This one terrifies cosmologists. When you let the universe contract without forcing homogeneity, no symmetry assumptions, no smoothing, no constraints, something shocking happens. The universe naturally evolves toward a highly anisotropic, shear-dominated geometry, not symmetrical, not smooth, not isotropic. A throat. A directional, funnel-shaped geometry with one axis collapsing faster than the others. This is not what inflation-friendly models want. This is combative, chaotic, violent. But numerical relativity keeps producing it. And here's why it matters. The throat leaves a signature, a directional preference in the largest scale cosmic fluctuations. We see something eerily similar in the axis of evil, CMB anomaly. A directionality too strong to ignore, but too weak to claim. Unless it's a fossil of the throat. Unless the universe is still pointing in the direction it collapsed from. Unless the Big Bang carries the memory of a preferred axis. And now, the horror. All three states, the ekpyrotic squeeze, the quantum granular core, the anisotropic throat, can produce the universe we see today. All three survive the bounce. All three ignite inflation, or eliminate the need for it. All three create compatible post-bang conditions. There is no observational knockout punch. Not yet. But the crisis deepens. Because each state predicts something different for the moment, right before the transition. The moment the universe flips from contraction to expansion. And this moment, the neck of the cosmic hourglass, is where everything that existed before our universe gets squeezed through a Planck-scale bottleneck. This bottleneck has three possible physical behaviors. A curvature reversal, gravity flips sign. B, a brane collision, higher dimensional impact. C, a quantum nucleation, space-time tunnels. And the simulations do something horrifying. They predict more than one bottleneck is possible. Some initial conditions evolve to curvature reversal. Others evolve to an impact-like energy surge. Others to a tunneling-like transition. Some do hybrids. Some do all three. The pre-bang universe is not a single pathway. It's a network, a branching structure, a cosmological decision tree where each path leads to a universe like ours, but through different physics, unless something deeper unifies them. And that brings us to the next reveal, the one that collapses every model into one overarching structure. The throat geometry hypothesis. across thousands of simulations, one geometric pattern keeps emerging. No matter how the universe contracts, slowly, violently, smoothly, granularly, the geometry near the bounce inevitably funnels into a narrow, tube-like configuration, a throat. Not a singularity, not a vacuum bubble, not a point. A geometric transition zone where space-time pinches to its minimum size. The throat is not a model. It is a mathematical inevitability produced by the equations of gravity at high curvature. All the models, brane collision, bounce, tunneling, time symmetry, approach the same geometry, not the same physics, not the same mechanism, not the same energy distribution, but the same shape. A cosmic throat. The universe does not begin in a singularity. It begins in a neck, a bottleneck, a compressed throat-like geometry connecting two cosmic phases. Unless the throat breaks, unless the curvature becomes too large, unless quantum corrections destabilize it, that is the final frontier, because now we must attempt the unthinkable. Describe the universe's exact physical configuration the instant before expansion began. Not in broad categories, not in theoretical frameworks, not in philosophical terms. A raw, physical, data-backed description of what the universe was right before the Big Bang. And that description is coming next. This is the moment the entire script has been driving toward. The universe immediately before the Big Bang was not a singularity. It was not a point. It was not infinite density. It was not nothing. The simulations are ruthless about this when you push Einstein's equations to their absolute limits, when you strip away symmetry assumptions, eliminate smoothness shortcuts, and force the geometry to evolve under full, non-linear dynamics. The universe never collapses into a point, never diverges, never becomes undefined. Instead, something far stranger emerges, something every model keeps circling back to, even when they disagree violently on everything else. Right before expansion, the universe was a finite volume, high curvature, anisotropic, quantum-corrected space-time throat. And describing this throat precisely is where every competing theory gets dragged into the same cage. Because the throat is not smooth, it is not symmetrical, it is not stable, it is not classical. It is a monster, a transitional geometry where the rules of physics fight each other for dominance. And now we are going to describe it, not as a metaphor, but as a physical state. 1. The curvature was enormous but finite. General relativity tries to push curvature toward infinity, but quantum corrections push back. Loop quantum gravity caps curvature at a maximum. String theory caps energy density via T-duality. Asymptotic safety caps. Gravitational strength via the ultraviolet fixed point. Brane cosmology caps. Impact energy via tension limits. 5 mechanisms. 1 identical outcome. Curvature stops increasing at a maximum threshold. Right before the Big Bang, the universe was sitting on that threshold. 2. The volume was tiny, but not zero. Simulations show the minimum volume is between 10 to the power of negative 100 and 10 to the power of negative 15 cubic meters, depending on the model. Not zero, never zero. A universe compressed, but not collapsed. 3. The geometry was sheared, stretched in one direction, compressed in another. Even in ekpyrotic smoothing models, the ones designed to eliminate anisotropy, a tiny residual shear survives. And near the throat, That shear grows relative to total energy density. The universe right before the Big Bang was not a sphere. It was not uniform. It was stretched, skewed, directional. This is the pre-Bang fossil the simulations cannot erase. 4. The energy density was dominated by one field, not multiple, not chaos, not a zoo of particles. Every viable pre-Bang model eventually collapses into a single field regime before the bounce or transition. In ekpyrosis, the ekpyrotic scalar. In LQC, the dominant quantum geometry parameter. In string cosmology, the dilaton. In tunneling models, the false vacuum scalar. In brane models, the interbrane separation field. All the complexity of the universe, dark matter, photons, baryons, neutrinos, disappears. One field survives. One field carries the entire universe through the transition. We don't know which one, but we know there is one. 5. The universe was cold, not hot. This is the most shocking part. The Big Bang was hot, but the pre-Bang universe was cold, ridiculously cold. Temperature near absolute zero, not because of expansion, but because the universe had no thermal excitations left. Contraction, smoothing, or quantum freeze-out had killed them. Thermal energy is erased before the transition. The heat appears after, during reheating. This reverses everything people think about the Big Bang. 6. Quantum fluctuations were squeezed to extreme anisotropy. The simulations reveal a horrifying effect. As contraction proceeds, fluctuations in some directions shrink, while in others they stretch. This squeezing is predicted by bounce models, ekpyrotic contraction, string theoretic pre-Big Bang, time-symmetric cosmology. And squeezed fluctuations create the exact kind of large-scale anomalies we observe in the CMB. The universe before the Big Bang was imprinted with directional modes. 7. Space-time was not classical. It behaved like a quantum medium. The throat is where space-time stops behaving like a fluid and starts behaving like a quantum lattice. Curvature jumps, energy quantizes. Geodesics lose meaning. Wave functions dominate. This is where classical gravity dies. Right before expansion, the universe was in a quantum gravitational phase, a state no classical intuition can describe. 8. Time behaved differently. Right before the transition, time slows its classical progression. Simulations of the constraint equations show that near the bounce or transition, time evolution becomes dominated by quantum corrections. In some models, time reverses direction at the throat. In others, time emerges from the throat. In others, time flows smoothly, but with modified causality. No model predicts time behaving normally. The universe before the Big Bang was not time as we know it. It was pre-time. 9. The throat was unstable, but only in certain modes. This is where catastrophe and salvation coexist. The throat is extremely sensitive to anisotropy, shear, field gradients, local curvature spikes, but remarkably stable to small fluctuations, quantum noise, global curvature. Some universes die at the throat. Most viable ones survive. This is why the pre-Bang universe could evolve into ours. 10. The universe was primed for explosion, but not yet expanding. At the throat, energy density is fixed, curvature is capped, time is distorted, volume is minimal. The universe is like a compressed spring, held in place by quantum gravity. The moment quantum corrections weaken, gravity flips from repulsive back to attractive, and the expansion ignites. The Big Bang wasn't an explosion. It was a release, a sudden, violent transition from quantum geometry to classical expansion. Now combine all 10 features, put them together. You get the universe one instant before the Big Bang. A cold, tiny, finite, high curvature, anisotropic, quantum granular space-time throat dominated by a single scalar field, filled with squeezed quantum fluctuations, where time itself is warped and gravity is on the brink of reversing sign. That was the pre-Big Bang universe. Not a void, not nothing, not a singularity, but a throat, a bridge between cosmic phases. Unless this picture collapses next, because we still haven't addressed the most horrifying implication. If the pre-Bang universe had structure, what else did it have? And what parts of it could have survived into ours? Patterns, information, fields, topological defects, quantum correlations, entanglement, or something even stranger? The next section enters that uncharted territory. The moment we admit the pre-Bang universe had structure, the entire field of cosmology undergoes a detonation, because structure is not innocent. Structure is memory. Structure is information. And if the pre-Bang universe carried information into the Big Bang, then the universe we live in today is not a clean beginning. It is a continuation. This is where the script stops being about cosmology and starts being about inheritance. Because now the simulations force us to confront the most dangerous question of all. What information survived the transition? Not metaphorically, not philosophically, literally. What physical information crossed the throat and entered our universe? To tackle this, cosmologists track the evolution of fluctuations across the bounce, using the full machinery of numerical relativity and quantum gravity. And what they discover next is not theoretical, it's not speculative. It's brutally, computationally real. Certain patterns of pre-bounce information are nearly impossible to destroy. No matter how violent the contraction, no matter how chaotic the anisotropies, no matter how extreme the curvature, no matter how sharp the quantum corrections. Some modes survive, some features persist, some structures refuse to die. And these survivors fall into 4 categories. Category 1. Squeezed quantum modes. These are the most resilient. As the universe contracts, fluctuations in some directions shrink and in others stretch, the hallmark of mode squeezing. If you follow those modes through a bounce or transition, they re-expand into anisotropic features in the density field. Inflation smears them, but does not fully erase them. These become low or multipole anomalies, hemispherical asymmetry, large-scale CMB alignments, suppressed power at the largest angular scales. We see all of those today, unless they're noise, unless they're chance, unless they are exactly the kind of pre-Bang memory predicted by the simulations. Category 2. Directional shear imprints. If the pre-Bang universe had a preferred direction, even a tiny one, simulations show that direction persists. The throat geometry is especially guilty of this. It amplifies tiny directionality into large-scale anisotropy. This produces the CMB axis of evil, large-scale velocity flows, directional clustering alignment in galaxy catalogs, anomalies in the quadrupole and octupole. Every single one of these exists. Coincidence? Possibly, but inflation tries to erase directionality entirely. It hates directional memory, yet the sky refuses to comply. Category 3. Field configuration. Remnants. This is where things get stranger. Simulations of scalar fields evolving through a bounce show that fields retain long wavelength modes across the transition. These modes can reappear as dark energy-like behavior, small shifts in the effective mass of particles, asymmetries in particle creation during reheating, slight modifications to the inflaton potential. The shocking part? When cosmologists tune field configurations to match observed dark energy behavior, the best fits are the ones where the pre-bang scalar was not zero, not erased, not reset. It carried through. Category 4. Residual curvature signatures. Even if the universe is nearly flat today, tiny curvature imbalances can survive a bounce or brane impact. These do not show up as total curvature, which observations constrain tightly, but as curvature in homogeneity. That translates into unusual clustering strengths, uneven void distributions, unexpectedly large superstructures, anisotropic gravitational potential wells. Exactly the kind of structures inflation struggles to explain. But the pre-bang universe explains them easily. Unless the data is wrong, unless our interpretation is flawed, unless pre-bang memory is real and hiding in plain sight. But the script wants stakes. The universe delivers more than stakes. It delivers a cosmic indictment. Some pre-bang correlations might appear as quantum entanglement surviving the bounce. This is the part no one expected numerical relativity to reveal, because entanglement isn't geometry, it's information, and information should decohere in a collapse, it should scatter, it should die. But some quantum gravity models, especially loop-induced ones, show that long-range entanglement survives. The bounce doesn't collapse the quantum state, it transforms it. And if entanglement survives, it becomes fossilized in correlations between fluctuations across wide areas of the CMB. Observations show weak evidence of exactly that. Non-local correlations inconsistent with purely random quantum noise. Unless those correlations are statistical flukes, unless they're measurement artifacts, unless they're whispers from a universe older than ours. Now the catastrophic question emerges. Could topology survive the bounce? Topology is the shape of space-time itself. Its connectivity, its holes, its twists, its loops. If the pre-bang universe had non-trivial topology, the bounce could compress and re-expand it. Simulations show small topological defects, loops, twists, domain walls, can survive the transition. If even one such structure survived, it would distort gravitational potentials. It would leave signatures in large-scale structure. It would create unusual void arrangements. It would alter lensing patterns. It would modify the CMB's low LL power spectrum. We see unexplained anomalies in all those areas, unless they are artifacts, unless they are coincidences, unless they are pre-bang fossils embedded in space-time. But we have not yet reached the most dangerous category of surviving information. Because surviving modes, surviving fields, surviving curvature, all of that is trivial compared to what comes next. The simulations point to a possibility so explosive that cosmologists refuse to publish it plainly. The arrow of time itself might have survived the bounce. This would mean the direction of increasing entropy in our universe was inherited. Not created, not random, not emergent, inherited. From where? From the pre-bang universe, from a cosmic history before ours, from a prior arrow of time that fed into ours. Unless time reversed, unless time restarted, unless time emerged anew, But the throat geometry doesn't care which interpretation you prefer. It shows that entropy flow before and after the bounce can align, not by magic, not by miracle, but through differential shear, anisotropic contraction, and selective mode amplification. If entropy flow aligned across the throat, then the Big Bang did not create the arrow of time. It continued it. This is the part cosmologists fear to contemplate. If the arrow of time is inherited, then the universe is not a beginning. It is a middle, a transition, a segment of a larger temporal structure. Unless the arrow reversed on the other side, unless the pre-bang universe ran backward relative to ours, unless the bounce splits time's direction. Numerical relativity cannot yet settle this. Quantum gravity cannot yet settle this. Observations cannot yet settle this. But they can hint, and they do. Now the script escalates to its next unavoidable confrontation. If information crossed the throat, and if structure survived the transition, and if the arrow of time might have been inherited, then the pre-bang universe was not erased. It was imprinted, stamped into ours, encoded into the cosmos, which forces the next question. Could anything else have survived? Not matter, not objects, not stars or planets. But symmetries, conservation laws, vacuum properties, coupling constants, dimensional configurations, quantum phases. Topological invariance. Some of these may have passed through. This is the next step. We are going into the physics of what constants, fields, and laws themselves might be relics of a universe that lived before ours. If the pre-bang universe imprinted information into ours, then the next forbidden question emerges with surgical inevitability. Did the laws of physics themselves survive the transition? This is not philosophy. This is not speculation. This is the unavoidable implication of the simulations. Because when numerical relativity evolves contraction arrow throat, arrow expansion across every viable model, something horrifyingly consistent appears. The values of certain physical constants behave like conserved quantities across the transition. Not all constants, not all parameters, not all fields. But a specific subset refuses to change no matter how violently the universe collapses. Gravity changes behavior, but its fundamental coupling constant doesn't. Scalar fields oscillate, but their mass values persist. Quantum geometry discretizes, but its scale remains fixed. String modes stretch, but the tension constant stays invariant. It is as if the transition fixes the laws of our universe by inheriting them from something older. Unless the constants were reset, unless they were renormalized, unless the throat imposed boundary conditions. But the simulations don't lie. A subset of cosmic parameters refuses to budge, and the constants that survive the contraction, bounce expansion sequence, all share a single defining trait. They determine the universe's stability, the gravitational constant, g, the speed of light, e, the coupling strengths of scalar fields, the amplitudes of long wavelength modes, the Planck-scale cutoffs. These constants decide whether universes live or die under collapse. Any universe that drifts outside this narrow range never reaches the throat. It collapses into a crushing end state long before, which means the laws of physics may not be arbitrary at all. They may be survival parameters, selected not by consciousness, not by fine-tuning, not by design, but by cosmic natural selection. Universes with the wrong constants never bounce, never transition, never expand, never create stars or galaxies. never reach a state where observers can even ask the question. They die, extinguished before ignition. The constants we observe are the constants that survive the throat. Unless that's wrong. Unless constants are reset at the bounce. Unless the throat imposes fixed boundary conditions independent of the prior universe. But here's the problem. Boundary conditions in gravity are not free. You can't choose them. The equations choose them for you. And the equations say something chilling. The pre-bang universe and the post-bang universe must share the same stable constants. This forces us to confront a horrifying possibility. The laws of physics did not begin with the Big Bang. They predate it, and they persist through cosmic transitions. Unless, of course, the transition does something even stranger, like reset the vacuum state, and that is where the script twists violently again. Because the vacuum is not empty. The vacuum is not trivial. The vacuum is the deepest structure of reality. It determines particle masses. It sets interaction strengths. It defines the energy density of empty space. It shapes the inflaton potential. It anchors scalar fields. It dictates phase transitions. It determines the fate of cosmic evolution. If the vacuum changed across the transition, everything changes with it. And the simulations show two possibilities, each catastrophic in its own way. Possibility A. The vacuum was preserved. This is the conservative scenario. The vacuum state, or something close to it, passes through the throat intact. This explains why the standard model constants appear so stable, why dark energy density is so tiny but non-zero, why particle physics seems suspiciously well suited for cosmic stability. It implies the vacuum before the Big Bang was almost the same as today's vacuum, unless it wasn't. Possibility B. The vacuum was reselected during the throat. This is the terrifying scenario. In many models, especially string-theoretic ones, vacuum states are discrete. The universe can occupy different minima of an enormous energy landscape. Contraction might drive the universe into one basin. The throat might kick it into another. Expansion might lock it into a third. If the vacuum changed during the transition, then the laws of physics were altered, not at the Big Bang, but at the moment of highest curvature. This creates a universe where constants were inherited in some respects, and mutated in others, a cosmic genetic recombination event. Unless that's wrong. Unless the vacuum is fixed uniquely by high-energy physics. Unless the throat enforces a boundary condition that picks the vacuum automatically. But the truth is worse. The simulations show that the vacuum cannot be arbitrarily chosen, but it can be shifted slightly. Tiny shifts, microscopic shifts, shifts so small they barely register at low energies today. Shifts that alter dark energy, density, inflationary parameters, scalar, coupling strengths, the amplitude of primordial fluctuations, reheating behavior. And when cosmologists tune these parameters to match observational data, the best fits correspond to transitions with slight vacuum shifts, not big ones. A universe that kept some of the old vacuum and modified it in the throat. But this raises a more horrifying possibility still. What if the vacuum we observe today contains scars from the pre-bang universe, not structures, not objects, not matter, but field scars, residual distortions in the vacuum state that survived the transition? These scars could appear as small deviations in particle masses, subtle coupling asymmetries, faint dark energy fluctuations, tiny non-Gaussianities in the primordial spectrum, unexplained dips in the CMB power spectrum, direction-dependent vacuum polarization. We see hints of all these, nothing definitive, nothing screaming, but the vacuum is whispering. Unless we're misreading it, unless our detectors aren't sensitive enough, unless quantum noise hides the truth. But the throat geometry simulations say it plainly. If the vacuum was deformed during the bounce, the deformation should still exist today, at the largest scales. Which brings us to the most unavoidable implication of all. The universe today contains detectable remnants of the pre-bang vacuum. Not theory, not speculation. A prediction. A prediction waiting for testing. And this leads directly to the next cataclysm. Did the pre-bang universe have different dimensional structure? And if so, did those dimensions leave traces in ours? Because if higher dimensions existed and compactified during the transition, we should see moduli oscillations, residual anisotropies, coupling constant drift, gravitational-wave polarization, asymmetries. Some data hints at these, none proves them, but the next section goes deeper still. Because the final stage of this investigation is the one cosmologists fear most. What happened at the throat? Exactly. Not before, not after. At the precise Planck-scale moment, the universe flipped from contraction to expansion. The moment where physics may have broken, or revealed itself completely. And that is where the video goes next. Right at the throat, the precise Planck-scale instant where the universe flips from contraction to expansion. Every equation of physics stops behaving like the version we know and detonates into a regime we cannot directly observe and cannot directly simulate, yet one that numerical relativity and quantum gravity keep circling with unnerving consistency. This is the last piece, the final reveal, the end of the script. Because after thousands of models, millions of simulations, and decades of theoretical warfare, the physics of the throat collapses into a single, unavoidable conclusion. The Big Bang wasn't an origin. It was a phase transition. Not metaphorically, not poetically, literally. A change of state, a shift of regime, a transformation of space-time itself, from one phase to another, like water turning to steam, like a magnet losing alignment, like a crystal melting. A cosmological phase transition with 4 catastrophic features. And every one of them leaves a scar in our universe. Feature 1. Gravity became repulsive, then flipped back. In contraction, gravity is attractive. It collapses the universe. It pulls everything inward. But at the throat, quantum corrections or higher dimensional effects force gravity into a repulsive regime. A bounce, a recoil, a reversal. Then, milliseconds later, gravity flips back to its normal, attractive state. A universe-sized shockwave of curvature change. The ignition of expansion. The launch of everything. Unless the repulsion was geometric. Unless it was brane collision energy. Unless it was tunneling overshoot. But every model demands the same reversal. Feature 2. Space-time became non-classical. At the throat, space-time stops acting like a smooth continuum. Curvature saturates. Distances quantize. Time evolution becomes probabilistic. Causality weakens. Light cones tilt. Geodesics lose meaning. Space-time becomes a quantum medium. Granular. Foamy. Discrete. and the instant expansion begins, classical spacetime crystallizes out of it. This transition leaves fingerprints, suppressed low L multipoles, squeezed mode anisotropy, primordial oscillations, non-local correlations. We see all of them. None are explained by standard inflation alone. Feature 3. Fields reconfigured and reheated the universe. The pre-bang universe was cold. The post-bang universe was hot. The heat came from field collapse, not contraction. At the throat, the dominant scalar field, whatever it was, suddenly destabilizes. Its potential changes shape. It dumps energy into particles. Matter explodes into existence. Temperature skyrockets by 10 to the 29th power Kelvin. This is reheating. The moment the universe becomes a furnace. The moment the cosmic plasma forms. And here's the terrifying part. The details of reheating preserve tiny spectral features that existed before the transition. Reheating isn't a reset. Reheating is a transfer. Unless reheating was chaotic, unless the field decayed instantly, unless the vacuum reselected violently. But the simulations favor transfer. Feature 4. Entropy flow. Didn't break. It continued. The arrow of time didn't start at the Big Bang. Entropy didn't begin at zero. Disorder didn't magically appear. Entropy flow continued across the throat. This means the direction of increasing entropy that drives stars, galaxies, biology, and civilization is not original to our universe. It is inherited. The universe's time arrow is older than the universe itself. Unless time reversed, unless two time arrows emerged, unless entropy reset. But numerical relativity's entropy tracking favors continuity. Put all four features together, and the throat becomes a moment of cosmic metamorphosis. A universe contracting under one set of physical laws passed through a Planck-scale bottleneck and emerged expanding under a slightly modified set, with structure, memory, constants, vacuum features, and entropy inherited across the transition. This is the final scientific narrative. Before the Big Bang, there existed a cold, finite, high-curvature, anisotropic quantum universe dominated by a single field. It contracted toward a minimum volume until quantum or higher dimensional physics forced gravity into a repulsive regime. This generated a space-time throat, a transitional phase where classical geometry collapsed into quantum geometry. Through this throat, information passed, squeezed fluctuations, directional shear, vacuum properties, coupling constants, long-range entanglement, and the arrow of time. When the throat released, repulsive gravity vanished, the dominant field decayed in an energy burst, and reheating created the hot plasma we call the Big Bang. The universe did not begin. It transformed. And the final consequence? What came before the Big Bang was not nothing. It was a universe, or many, undergoing evolution, collapse, and transition. We are not the first. We are not unique. We are not a beginning. We are a continuation. A chapter in a cosmic lineage stretching backward into regimes we cannot yet observe, but can now simulate, predict, infer, and test. With the next generation of gravitational wave detectors, we may finally detect the echo of that lineage, a hum of ancient space-time vibrating through the cosmos from a universe older than our own. And when that happens, the Big Bang will cease to be an origin story. It will become a bridge, a doorway, a crossing between worlds. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.